before David reminds me again about the start recording. Now I am recording. Oh, yes, yes. I think the voice should be included, yes. So, Reinhard, can you say something quickly? Just to make sure we're recording the audio?
Yes, 1, 2, 3, 4.
Okay, good. Yes, I can hear you. And so can OBS Studio.
Sehen Sie hier nichts. Aber es ist deutlich eine Flagge, kommt irgendwann in den nächsten 10 Jahren zu einem vernünftigen Set. Genießen Sie es einfach. Ich nichts erzählen kann. Ich wollte.
Oh, yes.
Aber wenn ich das mitschauen, stimmt der nicht mit.
Es ist nicht abgestimmt.
Ja,
Also, die ersten Mal haben Sie jetzt
also mit meinen Schülern sind wir Samstag ab. Ja, eben.
Das ist sehr gut.
Ja,
Also mit der
Wir haben tatsächlich bei uns in der Gruppe schon überlegt,
Die sollen einfach mal mit dem
eher das es ist so, und eigentlich ist es auch gut, wenn man diesen Freiraum nutzt, um mal ein bisschen rumzuprobieren. Also wir sind auch gerade parallel dabei, mehrere Modelle aufzubauen, um mal zu gucken, welches am besten läuft. Das erfordert aber natürlich dann auch ein bisschen Freiraum und Zeit, um das zu machen. Oder? Nee, ja, das ist schon. Ja, genau.
Ja.
So Professor Borges will do some explanations about the midterms for his students. I shortly considered we will join the midterms of the Taiwanese students, but well, we'll see. After that, we will continue with the lecture.
Okay, good.
If Borges isn't doing stuff, I'm prepared for some dynamics. But let's see.
Wenn wir uns da entscheiden, schon mal Roboter holen und du brauchst 2 Installationen. Schon da. Das war
Ja, auf jeden Fall.
ja, das hat auch zu Hause nicht geklappt. Das dauert halt so 5 Stunden.
Yeah. So everybody should set up a TurtleBot, physical TurtleBot. Everybody should have received or should have retrieved an SD card. Not everybody should have retrieved one of those SD cards. It will take time. You need to install the Ubuntu operating system. You need to install the ROS. You need to install some additional stuff. Learn how to use the camera and so on. It cannot be done one night before submission. You can book the TurtleBots and
Ja, nicht ohne Laptop. Und hier geht nicht, weil das Internet ja nicht haben.
Ja.
Sie können das vor auf jeden Fall.
Okay. Das läuft.
Then you just go there and get one of those.
Excuse me, sir.
Yes,
Sir, what is the dead time for this summit 2 or summit 3?
2 weeks.
Like almost done or still we have time?
In 2 weeks, you should be finished.
So that means like this week will be the last week.
In 2 weeks.
From now to 2 weeks future, you mean?
Yeah.
We can say like in the middle of May, you mean? It should be like February.
Let's do some proper calculations. So, May 1st, 4th, should be 11th.
11 May, it should be.
Yeah.
Yeah, even if
So, but there will be another task afterwards. So you should not spend too much time on this because you will also have to work on the other tasks. And the next task is the climbing robot. The simulation of a climbing robot. You need to do design of the robot. Well, you could use what you like Professor Baltus, I think last time he demonstrated this with the Taiwanese bear. You could use that, but you could also use some other robot design, or you do your own design. And then, of course, you need to prepare some.
Okay.
Then you should.
Then I'll get started now, if that's okay, so we can get through the midterm. I shall share my slides with Ostfalia as well. Reinhard, can you give me like presenter? Or make me a presenter or something?
Ich habe sonst einen Banner.
You can present it now. And if it's easy, we also do the assignment, the midterm. Jetzt geht auch ohne.
Es gibt Sets im Internet. Also das habe ich jetzt hier gemacht.
I
Also
think
das
you
war
can
eigentlich
see that one already.
So 10.000 Bilder.
Jetzt haben sie das.
Machen das geht da noch raus?
Das cool aus. Macht das wirklich.
Ach, Sie auch.
Now you should be able to see the screen. So the following are comments about the midterm for my class at NTNU in complex motion planning. Because I decided to make some changes this year. Due to the use of ChatGPT and similar systems by the students, 2025, I believe, was kind of a watershed because now ChatGPT was actually good enough to answer most of my exam questions, which it wasn't able to do before. So we had too many students just cutting and pasting the questions into ChatGPT, especially the paid version. So this year then I decided to change the format. So this will be the format of the midterm, which for my students starts today and will end next week with the oral exam. So now there will be 3 parts. One, I will give you 3 papers from the research literature that you are supposed to read in order to be able to understand the topic. For this particular midterm, we are looking at search-based and probabilistic motion planning algorithms. So that's the general outline of the midterm questions. And so today I released the 3 research papers. I'll talk a little bit about them. Then I ask you to implement a probabilistic search planner and implement it before Friday for a rock climbing robot. With that, you can then compare it against the search-based approach and sort of look at the runtime, which would be the main runtime, and memory consumption of the 2 planning systems. And then next Monday there will be an oral exam where I cover the research literature, the implementation, and other material that we covered in class. Let me just fix that. And that will be at 2 o'clock. So we've talked a bit about motion planning already. So I selected 3 papers from the research literature. One is motion planning for climbing mobility with implementation on a wall climbing robot. That one presents a search-based approach to motion planning for a wall climbing robot. The second one is a very seminal paper by Laval and Kufner in motion planning. It's the let me just add the title. This was one that introduced rapidly exploring random trees, and it's a very influential paper. I think if you look at Google Scholar, it has like 5,000 citations or something like that. It's a very pragmatic approach to motion planning, used in several other domains. And the third paper is focusing a bit more on dynamics and kinematic constraints as far as the search planning is concerned. It's by Latome from Stanford University, also a very eminent research in path planning and motion planning research. So that will be motion planning for a 3-limbed climbing robot. So you'll have to take one of these algorithms and implement a version of it for our simple climbing bear. The papers are available on the Discord channel, and the climbing bear is available on the link here. So you want to implement a proper motion planner for that robot. The climbing bear has a couple, if you look at the source code, there is a couple of routes that you can try with your robot to see if it's able to climb to the top or not. And then before Friday evening, you must do a submission, which is done using a private GitHub repository. So create a GitHub repository, submit all your code, include all the graphs, histograms of your research, and then include a 3 to 5 page write-up about your implementation and research. And that can be in LaTeX or OpenDoc format, like ODT format. Also include the honesty declaration, which I also posted to the Discord channel. Which basically just says what tools you used while doing this particular assignment. So your name, your student ID, the other members of your group, who you work together with. You certify that this is your own work, and then you list all the external sources that you used in your implementation, including part of the code that you copied from me, part of the code that you found on the internet, OpenCV library documentation, for example. And in particular, if you use ChatGPT or any other AI system, then you need to list the prompts that you were using and all the code that was written by that system. And
By the way, this is pretty
in my
final.
case, however, I want to warn you that you won't get any marks for code or research that you cannot explain during the oral exam. So if you copy and paste the code from ChatGPT, even if it works, if you cannot modify it, if you cannot debug it, if you cannot explain it, then you won't get any credit for it. Okay? So we will try this new version of midterm for 2026. I think it has potential. I like it because, in a sense, all of this stuff is what you should be doing as graduate students or fourth year bachelor students anyway. You should be reading the research literature, you should be understanding the research literature, you should be able to create some artifact, some program, some implementation based on what you read and understood, and you have to be able to explain your work to your peers or your professors. So in a sense, it's a small version of the graduate student and higher level undergraduate student experience. Okay, good. So any questions about that? Oh. Can I close this then? Then some comments to all the students. Actually, let me just sure that this is all clear here. So you guys have all understood the format for the midterm? Yes, you? You understood what you're supposed to do by next Friday, next Monday? Yeah, yeah, yeah. Okay, good. Benson? Yeah, read 3 papers, implement 1, and then evaluate the performance on the rock climbing robot. And then answer questions about it. Well, all 3 papers describe an algorithm for climbing robot. Or all 3 papers describe an algorithm that can be used for climbing robots. Yeah. But compare it to the other ones. So you have to read all 3 papers. On the simulation, if you want to, you can do Python. This one here is written in TypeScript. So you can use this one if you want to. If you don't want to, you can implement your own version in Python. Yeah, yeah. Because on Monday you don't actually have to work that hard, you just have to answer questions. So one implementation is due on Friday, the other one is due on Monday after that. Which file? The link is in the presentation that I posted. The link is here. Huh? You only need it for the rock climbing robot, yes. Everything is posted except the slides here, I think. Now, I'll let you use Python. I really hope that you can help me though with the TypeScript implementation of the climbing bear, because we do have, or me personally, I have a problem, but if your professor has a problem, then all the students have a problem too. That's just the way it goes. So the problem is that we are running the FIRA competition in Canada in July, is it Benson, 15 to 19 or something? Yeah. So there, usually we have the teams from all over the world come to Canada, and we also have we have quite a few participants from Iran, which, if you may know, at the moment is in an actual hot war between the United States, Israel, and Iran. And so that means that the team from Iran won't be able to travel to Canada, because there's no flights out of Iran, and even if they could, it's very hard to get a visa for Canada. So it's extremely unlikely that they will be able to go to Canada. So what we did, now the suggestion by the Iranians is that they want to host what we call a Simul Cup, which is something that I did in 2020 because of COVID. Nobody could travel at that time, so we basically allowed different labs throughout the world. And the Eurocup Sprint, for example, it would all happen at the same time. So there would be like one referee in Korea, and one referee in Taiwan, and one referee in Russia, and one referee in Canada, and one referee in Iran, and they would all set up the robots, and they all blow the whistle at the same time, and then they all run. In different parts of the world, they would run the same competition, which was actually quite a bit of fun. It still gave the feeling of community to everybody, even though we couldn't travel. So the problem is now that Iran chapter of FIRA wants to run this Simul Cup idea again, but I am not in favor of that because I really think it is too dangerous. If you have followed the news, Sharif University in Tehran was bombed. So there's like big explosions there. Tehran Tech University was bombed. And now I think it's just not ethically possible. I just can't bring myself to say that we should run a competition in Tehran with hundreds of participants all in one place. If a bomb drops there, then basically a huge number of FIRA participants would be injured. At the minimum, best case scenario would be that they are just injured. Worst case would be even worse, right? So I said, no, I don't want that. But then now they say, well, but we could do it. We think we can do it. And I'm sure they could do it, but I don't think it's a smart thing to do. I think the risk is just too high. So I have to get them an alternative. They want to take part in it, so now I think, okay, we're going to be doing this web simulation of a climbing bear, and then this will be a simulation competition. So they don't need to install anything. It runs on the web server, on the browser. So they can run it on their laptop at home. They don't need to travel all to one place in Tehran where all of them are together.
So you kind of stole my idea about the midterm. Anyway, the final exam will be similar to that. So you may carefully watch the midterm. You may want to talk with the Taiwanese students about their finding. Oh, sorry.
Yeah. So anyway, so that's the plan right now. So I need to get this simulation done very quickly. It can already do kinematics and everything, and now I need to add WebSocket support so that you can run a Python or any kind of application. You talk to the browser, the robot will climb, and then I need to figure out a way in which we can score it. And then it'd be kind of cool. Then anybody can take part in this. And right now, this simulation only uses the kinematics. I also would like to introduce the dynamics, which I did last year with MuJoCo. And so first thing I'll do is I introduce the MuJoCo simulation into this using WebASM, and then hopefully I get it all done and packaged within the next 2 weeks, and then we can publish it and have it as an official competition for the simulation leagues. And then hopefully hopefully the whole FIRA community will stay safe. Of course, all of you stay safe too. It's just they're actively dropping, or they used until a couple of days ago, there were explosions in Tehran. So their risk is obviously a bit higher than ours at the moment. Even though we're in Taiwan and China, so who knows what's going to happen there. Maybe we need this for the Taiwanese students next, if we're unlucky. So anyway, yeah, so that's the comments that I have about the midterm. So it's quite important that we get this done quickly, and if you can help with that, then great. Then the whole FIRA community will be grateful to you. Okay, good. And don't forget Monday oral exam. Okay, good. Then Reinhard. Hello? Oop. Okay, so yes, for the midterm at Ostfalia, they will be implementing the card trick on the Turtlebot, and NTNU students will provide the card detector, which they have implemented already. David actually did a nice job. We can share the screen. Oh, I cannot. Other videos. Share. Yeah, so this is what David implemented so far, and working quite nice. Spades 4, 84% accuracy, Queen of Hearts. Heart Queen was not quite right. 9 of Spades, 8 of Hearts. Yeah. So you trained this on the Blender files at all, or just your own pictures? Okay. Okay. Yeah, I can play the video again.
Okay, Jackie, we're back.
Okay, yeah, I'm just playing the video again here by one of the students that implemented the card detector, which works quite well. The top here, it's like perfect, right? The Spades 4 is 97% accuracy, and the second highest hit is 0.9%. Hearts, Queen Hearts, 90%. 60%, and Heart 8, 51%. But we got those quite accurate. So this is done using a simple convolutional neural network. That in the small language model robotics course, we're now trying to take that particular network that works with good accuracy and prune it down into something much smaller so that we can run it on a Raspberry Pico 2 if we want to. Even though this one now is actually running on an Android phone, and that means the phones nowadays are actually quite powerful. Like there's no real reason to prune the network if you run it on an Android phone. It's easily fast enough to do that. But we just want to prune because we want to look at running even bigger networks on the phone in the future. We don't want to waste resources. Also, I need to take a screenshot, I guess. Oh, okay. I just take them because otherwise I keep forgetting about it. But now, how come I don't? Yeah. If you want to see the video, it is actually on the Discord channel for complex motion planning, but I cannot share video files on Big Blue Button.
You could share your screen.
I did that already. I showed the video twice now. You want me to show it again?
No, because you said you can't show a video, but
Okay. Our Discord channel is here, if you want to join that. So now for today, I want to give you another task, starting with, or in the area of randomized motion planning, and we want to show why things are more subtle every time you're dealing with randomized processes. Every time you're dealing with statistics, there's often a lot of surprises, lots of paradoxes. Your gut feeling, your intuitive reasoning is often not very good when dealing with probabilities. So let's have a look at one of those to show how and why we need to be sometimes more clever than we expect. So you should pick a partner with Ostfalia University now, and this particular assignment will only take you about 20 minutes to implement. It's fairly simple, but it allows you to work together in a group, and it'll get you started on thinking about rapidly exploring random trees. So the question is, you have an environment, let's say 10 meters by 10 meters, right? And you have a small, very small robot, a wheeled robot, and it's really just a dot. And sure, let's put in some obstacles. Yes, some obstacles. Rectangles or polygons, whatever you want. Just put them in the environment, so then not the entire space is traversable. There's some obstacles in the way. Okay? Now, this kind of scenario would be similar to what you have with a vacuuming robot, because now what you want to do is you want to implement an algorithm that explores this particular environment. But the problem is, your robot has very noisy sensors. So you cannot detect the obstacles.
Also ich habe jetzt auch deswegen relativ schön, also meine nicht mehr
You cannot detect the walls. And you cannot detect or determine your position. So all you can do is you can drive forward.
Jackie, could you focus on the whiteboard you're using?
Yeah.
Das ist auf jeden Fall, das ist eine so gute Lösung.
Okay, just wait. Actually, you can post on the big blue button yourself, looking for a partner.
So we should have enough time for Taiwanese.
You know this moment and should be fresh, should be sleeping well, so you can understand. Okay.
Yeah.
Maybe it... Because this is old. What is old?
Oh, that's good. Do you have a Do you have the Roomba? Roomba vacuum cleaner? Okay, I'll give a very expensive one, yeah. Okay, if you would have the shower run, if this is right. The returns. No, you don't snack anything. Just. How much? Because this is one of the reasons to have this more sophisticated roads, because they only pass one, they finish very fast. If you move randomly, you cover the same area a couple of times, just to make sure you cover every, or almost every area. Room 151, but it's your group. We don't have an SD card for every one of you. Yeah, by the way, on the groups, we have at least one group with 5 participants. Please make sure you only have 4. Well, 4 plus 1 Taiwanese. But if it's 5 of us, I will resolve the issue unless you do. So only 4 participants per group. There's one guy who's on his own. You have an SD card?
Other 2 participants
Disappeared. Yeah, okay. So please make sure the others quit the group. Because, the groups are okay, so you send me, yeah, please contact them or send me an email about them not being active. And then we'll wait to give them about 3 days to answer. After that, I can kick them off.
So here, I should add a command for vacuuming. We just assume the vacuum is always on, always running when the robot is driving.
Yeah.
It also starts yeah, of course. You should. Sometimes they have limitations when it comes to the size. It could also be broken. It shouldn't take that long. It takes some time.
Yeah, of course, that's when it's slower, but faster.
Otherwise, it should.
Then we have to see what kind of shape we want to use for the environment. Not different ways. I usually do it as a list of obstacles and the width and the height. We can also use it as a 2-dimensional array and occupancy grid, just showing what parts are occupied, dirty, or clean. So in that case, the number that I need would be equal to width divided by the dimension and the cell height would be equal to mass ceiling divided by the dimension.
Maybe check the
And now we just specify the state of the height, so empty, dirty, obstacle. Anything else I need? No, I think that's it. Clean. I don't think I need clean because that would be here.
We show you that to the shirt, yeah? When you do this clearly.
No, we're gonna do this.
First time I see like that. Oh, there's something like we mentioned this, we have this day planning, 2 days, these days, something by this end. This is okay.
Some of us spend their savings to come here just to watch a video of someone.
And we say something and that one say something else. Everyone else reading with the lab, we can go.
Let's go. You don't
There
need
will
the
be one picture to sell. I don't think I want to do that. But that would work.
So many things we have also that report, we have to write something. We will do that.
Let's import the library. Random, okay. Rectangle. J times dim.
So you were asking about.
I think it's X1. Dim.
But I wasn't asking. I wasn't.
You explain.
Well,
the first question.
Clean.
We have
Colors equal.
the random.
Let's make it almost completely white.
This is the real turtle bot. This
Environment is dirty.
Yeah,
and we'll make it dirty.
and,
So maybe
we need to-
30, 30, 30,
Right.
30.
And we need to actually have cars, so there are no cars in
So let's
the,
make the
Well,
obstacle screen.
I thought everybody would have some cars.
And
Apparently not.
anything else?
Maybe you have something.
I made a mistake because those shouldn't really occur. Make that red.
No time.
we are certainly managing.
Okay. So they are in the lab, and you should start working with that.
We are working.
Well,
And
you should start working with that.
add patch R.
So the method would be clear to that.
Return
Yeah, this
So
this one will be
environment.
more serious. But whatever you use, you have to provide it. You should be.
Is it just scientific, is exactly that?
And let's draw the
There's
environment.
some grading assignments. I'm just talking about the grading assignments. This will be one of the grading assignments, the real turtle bot data capture. And it involves some thinking, because you have options to do this. How do you do the capture with this? So this is one, and the other one is the climbing robots station. Yeah.
Okay, so this is assignment three, that will be assignment B before. What about the midterm? Will we have?
This is the midterm, assignment for grading.
So far all dark,
You-
all dirty, maybe a little bit too dirty.
So
Let's go 70.
and it will be the magician.
It should be magic. Okay, so it will be the midterm. And only this showing and explaining, or we also write the exam report or something?
You also have to prepare documentation. You have to provide the software frame, which you use to do the trick. As I mentioned, it should have.
So now I have an environment, it's all dirty. Let's make a couple of them clean. Two,
If you use,
4, and 5 to 7 is equal to,
you don't have a copyright note in your code. Otherwise, it's not your work. So actually, that's fraud because you try to sell somebody else's code.
Alright. So only we have to show, there is no submitting, there is no link to
some
submit.
clean area in here. And now I can add my obstacles.
What May, I guess?
Um,
8 May. 8 May.
2 weeks from now. 11th would be the Monday.
Yeah, 11th will be the Monday.
Yeah, but
It will be.
it depends on what kind of type you are. If you do everything to the last minute, then let's say 4th of May.
If
If you
I mean, we can show you before.
So
Yes, well, that's one of the points.
Okay, I thought like that will be a course.
Yeah.
Let's just do that.
Ah.
XY is equal to random rand in, cell height, and cell width. And then all width is equal to random dot rand in. 1,
Then at first we
2,
know the time. The simulation. And we don't want to waste all the money for robots, which then are not finished. So do the simulation.
Is there,
Uh,
and then environment.
Provided by, no, there's no specific simulation. I,
Y.
one, Blender, well, Blender is not the simulation. Blender is for doing the Yeah. So you could use Majuku, you could use Gazebo. Huh?
Yeah, he said.
There are alternatives, but we don't have the equipment. So Majuku runs on almost every computer. We should have up and running because that was the entry.
Yeah. And it's basically we need to do the same as we showed in videos to climb.
Yeah.
Okay.
And whoever climbs to the top, okay. Grade A, grade B.
All right.
No, it's a little bit more complicated. You should be able to do to answer questions related to that. How did you do this? Why did you do this way? What kind of technology you have been using? You've been using the random approach. You have been using some other approach presented by Professor Borges. And then he may ask you about,
Let's
or
make
he
the
may ask
obstacles
you about.
blue. They look weird in green. Looks like a grass thing. So
It's the last week of the lecture, actually. Should be 8th of June.
The climbing one.
Yes, climbing one.
Okay.
So we would now focus on the.
But this-
Then we can focus in that, yeah?
Yeah, you could do it in parallel.
Yeah, something.
Yeah,
so,
something,
like,
yes.
just-
Yeah, well,
or like-
That's
and
actually the expectation is you have it's 5 ECTS, 150 hours for each of you, your group of 4. So that's 600 hours. It's 4 months. 4 months full
so
work.
why doesn't this
How
change?
Not doing that.
This is supposed, this is the workload supposed to be.
Or width?
And of course, during the semester, you do not have much spare time. So typically, semester workload is 900 hours. If the semester has 15 weeks, you just do a calculation. So you're ending up with 60 hours. And there's no work for earning and stuff like that. So we see if you're fit to do the job.
I think I forgot to
You
write.
may find an easy job, so later on, so get along with less work, but if you have a harder job, then you need to do 50, 60 hours a week.
Yeah.
And we practice for that. Now that's the theory. I know you guys, and some of you are very smart, so you will be faster. Check for yourself if you're one of the smart guys or if you have to work for a living. Okay, so 2 weeks for the magic card trick. You need to do some motion. You need to do some image recognition, which is only partly covered by the tutorial. You want to work.
So the cards actually should be laid on the ground or facing.
5 cards on the
And
table.
the camera will be able to detect all the edges and all.
Yeah, well,
So that
we'll
should
probably
be all, I think.
where you can see the card. It could be larger than this table.
Yeah.
You scan the card and you move a little further, scan the next one, you do this 5 times, then you move to the center. Could be. Well, maybe you have some other approach. Then
It's
in
related
terms
to
of,
the limits of the sensors. I mean.
no, you don't switch. You take, well, the human takes one card, puts it, because that's part of the human trick, puts it in front of that, changes it to the other hand, moves it back. Yeah, and then you will see, because of changing the hands, the card will turn by 180 degrees. And that's what the robot is supposed to recognize.
But actually, like when it comes to the card turning 580 degrees, it doesn't change anything. Right?
So this is the part where the brain
You need
keeps
to pick some cards that could be this magic card.
You'll limit, this is what the magicians also do. typically, they don't have the, well, depending on the trick, they don't have the entire set of cards, they only have some set of
Okay. Okay.
No. You need to write the documentation for
The thing is,
what you did, why you did it, and so on, which resources you use. And you do the same for the climbing robot. And you need to be able to answer questions. No answers, no points.
Vorlassen wir es doch weil die letzte Sache, wir mussten auch, dass wir Regie und so weiter auch arbeiten. Wollen wir das auch als Aussage zur Simulation auch das machen? Oder?
Wenn Sie die Zeit und die Ressourcen dafür haben, können Sie den Robot gerne aufbauen. Den kleinen Roboter aufbauen. Ja, wenn Sie das wollen, aber verzetteln Sie sich nicht. Machen Sie das richtig. Wir werden im Herbst anbieten eine Exkursion nach Bordeaux.
all right, here's our environment.
Da können Sie dann Software von Ihrer Simulation führen.
Dark. We want to position of the robot.
પછી તું આમ લે ને આ પાણી લઈ લે લેટર બોર્ડ નીકળી જાય એ કરે એક જ પછી આમાં સ્કેન કરે કે સ્કેન નહીં કરી એ મેન તો ન્યા લોન પાછળ લોજિક એ રીતે હા તો એક કામ કરો સપોઝ કાર્ડ આપણે આ બધું પોઝિશન થોડી કામ કરી દે આરામથી ખબર પડી કે મારી પોઝિશન એક ડિગ્રી વામ તો હિન્દુ ગણો પણ ઈ કરી વસ્તુ ઈ કે પહેલા જે આ એક મિનિટ બાદ પાછળ પાછળ ખબર પડી યાર તમારે લોગ જો કરે આ કાઢે હા તો આ પહેલું વસ્તુ બીજું છે ઈ ખબર પાડતા આપણે ઈ તારે મેજિક નું કીધું
Patches, circle, X, Y, size,
Blender મેજિક ટ્રીક દેખાડતા હતા ખાલી કાર્ડ્સ હોય આજે કાર્ડ નો કન્સેપ્ટ છે ને એને એમાં દેખાડતા હતી ખબર સિમ્યુલેટર આજે બોર્ડ આવી છે એમાં તો ટ્રેનિંગ રોબોટ કરી સબમિટ કરવાનું કે ન કરવાનું
and then if
તો
I
અત્યારે
can
રોબોટ
put in a line.
ઈ અત્યારે રોબોટ હતો રોબોટ હતું કીધું કે આજે ડેટા બોર્ડ કરવો તો કરી પછી કરજો એટલે એને એમ કીધું કે તમે અત્યારે ગમે કરો આ તો તમે શીખો હા એટલે ઈ કરવાનું છે એમાં એને કીધું કે પછી તમારે કેચઅપ કરવું જોઈએ રેકોર્ડ તો આ શું છે પણ રેકોર્ડ ની ખબર નહીં પડે હું એ દેવો તો વિઝા હે બોલે
Y,
ઓકે હું કીધું આજે ઓલા પૂછું છે ઓલા આજે તો ભાઈ પૂછવી
do we draw an arrow? A little bit too short. Shows it. I can make the figure a little bit bigger. So this one is 0.1. Like dimension by 2. And now I have a little arrow. Now I want to change my routine here. Because eventually I want to make an animation out of it, so I need to return the artist. That would be here.
It's the proper electric cars landing for the
Here's the figure, we draw the alignment, and then let's run 10 steps of our controller. So the robot, we can go forward. So that will be robot Q, then cos theta y, mass sine theta theta, return the Q, okay, and then turn. Make plus angle, return the robot Q, and here it's usually a good idea to normalize your angles, otherwise you end up with a lot of issues. So theta is theta plus angle. Theta greater than math dot pi. That was actually correct. Why did you?
Das ist die Möglichkeit, eigentlich.
Because we know all the things we do. Make sure we have 5 minutes.
And then And range forward. And let's say our dimension that we can drive is 0.1. And then we can put the robot.
Yeah. But to be honest, Sahil of another group, but yes, we found the same idea, separately arbeiten.
You work in your group. Talk with everybody.
All right,
But then,
good.
well, the
So
issue,
what have you
the groups,
implemented so far?
so maybe
You're
you
supposed to write this code, right?
off it.
Environment, robot driving around. You guys are supposed to implement the vacuuming robot like this, right? By now, for sure, because you started earlier than me, you should be able to draw these kind of figures. Right? Obstacle, dirty floor, clean floor.
Put the robot on the floor. It searches for 5 columns.
And then drive your robot around and see what you can clean. Yeah, kind of like this. You can do this too. Floor, yeah.
What to do?
No, blue is the obstacle.
If it,
The yellow one. Or the red one, I mean.
so the thing for the when is the human supposed to pick up the card? Pick up the card before the robot is ready memorizing the cards. So you need to have some kind of motion to make clear to the user, and maybe you have some kind of instruction to the user. When the robot flips it, then you're supposed to pick one card.
And after picking that card, we should also put that, and then robot detects which card you have pick that up.
Ich kann einfach
Oh, just take the card and robot will guess that the card will be
Here is a
as of
55 by
like
5 cell, clean
yeah, or
environment
like
now.
yes,
This
I
is
understand.
clean, this is dirty. This is where the robot is, this is an obstacle.
say say something in the program.
Now I understand fully loaded. Okay, that's 1, 2, 3, 4, 5 cards. Okay, first the robot have analyzed all the cards. You, for example, take down the last card, then your robot will move again from here to here, or he will just see the 4 card and you can missing card, or maybe he can tell you, okay, this card is missing. So
No, there's no missing card. You put it back.
you put it back.
Five of these.
Flip.
You don't know which of the 5 it takes. But the robot has to move, and it has to use the camera.
Camera angle for detecting this.
Are you in the Discord channel?
Okay.
I say to in the group if not the again send the photo and the description.
Maybe the video from the check-in.
Also, thank you. So sorry for
No.
Yeah, cleaning the dirty floor. Your mom will be happy if she sees you working on that. Okay, yeah, good. Correct, every cell that the robot drives in, the cell will be clean afterwards. Yeah. And then you need to work out a algorithm for how to control the robot, where it should drive. If you do this correct, you can sell 1 million robots, become very, very rich. If you do it poorly, then nobody will buy your robots. And so I forgot, here we can now, every position that the robot is in, we set it to clean. Robot driving. And now, I think I was a little bit too ambitious with 100 by 100. I think it uses a lot of memory. But okay, we'll leave it like that. And what I wanted to do was I can change the interval.
Una viene con la mano, quello che sono si deve di da prendere nel progetto per il schermo per
Dimension 0.5 here. It's okay, then draw the environment. Okay, so that would be so here my robot now is cleaning, you see. I mean, leave the trail. Here's the animation.
Reality. Whatever changing to be so. Let's not
But of course, driving straight forward is just forward is kind of silly. Because if I just keep going here, I'm going to hit that obstacle and then keep driving into the obstacle forever. So that doesn't make a lot of sense, right? It doesn't seem like it's going to be a very efficient algorithm for cleaning the room. So you need to figure out some other way. And yeah, I don't want to clean this anymore. Because I didn't set the dimension. Yes. Okay, so first I also need to make sure that environment int robot clear int robot is equal to clean. Draw the environment dimension. Oh, now I have to stop the robot from moving. If here it starts inside of the environment, so this is the only free space it has. Bad random roll of the dice. So let's change the number of obstacles to 5. This maybe 0.25. Okay, good. Didn't it drive? No. Could be that. Ah. How come MP is not defined now? Oh, yeah. Crashed for an unknown reason. Now here, we hit the obstacle. So we can drive a little bit where we hit the obstacle. I also need to add one thing which I forgot. greater than environment shape 0. I also have to check if it's running out of bounds. Or int new q1 divided by n greater than environment dot shape 1. Actually, this should be 0 here. Else, if it's an obstacle, and this is wrong too, because robot Q is x, y, and theta, so this should be 1, be 1, 0. Because new Q is x and y, yeah. So any ideas now for your algorithm, how you want to move around? Okay, that's pretty cool, that's very nice, but I didn't say that you had a touch sensor. Huh? Try it without the touch sensor first. So yeah, if you don't have a touch sensor, so you don't know if you ran into the obstacle or not.
How do I know I hit the road?
You can't. We'll first do it without the touch sensor. Correct, yes. You can't, so you have to guess. If you don't have a sensor, if you cannot tell if you hit an obstacle or not.
So, but do I know where is obstacle?
Hmm?
Do I know where is
No,
obstacle?
no.
So, if it's the car.
Correct, yes.
The obstacle.
No, that would be a little bit silly, right? If you just drive in a straight line, then you'll just get stuck. So, if you don't want to get stuck and you don't have a sensor, then what do you have to do? You have to do some kind of random pattern, yes. No, you just stop. Yeah, so even if you hit the obstacle at an angle, you don't bounce off, you just get stuck there. You don't have to simulate the bounce off. Correct, yes, yeah. Try the maximum guess for how to not get stuck in an obstacle. Yeah, this is kind of cool, but Oh, with the keyboard you can do that, yes, but without a keyboard. So you don't know where the obstacles are. Yeah. Yeah, what have you got so far?
Simulating, but I have the same issue. I thought that once we did one obstacle, we
Yeah.
went to like 0, 0, and then swipe.
Okay, okay. That can, if you have if you try and sweep like that, that's actually quite good. The interesting thing is if you do this without a touch sensor, then your only option is to throw in a couple of turns, right? So, okay, we can do that. Let's say we always move forward, and if with, let's say, 25% chance, we do a turn, and now the question is how many degrees we want to turn. Like, doesn't make sense to turn by 1 or 2 degrees. Very unlikely that this is going to get you out of a mess. So you can go math pi divided by 4, let's say from -2 to 2. Right, so pi over 2 is 90 degrees, pi over 4 is 45 degrees. So we turn from -90 to +90, but in steps of 45 degrees. Right? I would do that. And now I have more 100 steps. Now this will take a while on the Google Colab to execute. If you implement this on your local machine, it'll run a lot faster, and then what you actually realize. Can you just run that, Joanna? Like, just do a random turn. Yeah. Instead of touching the obstacle. And detecting the obstacle. You cannot detect the obstacle. Yeah. So you're not cleaning the floor at the moment. Oh. Let's see what the error is. Forgot the equal sign here.
Use.
I hope this animation will work the way that I expect it to. Then I don't have to run it again. Well, let's see. You. Okay. And you drive the line, okay? Right, but you still detect the obstacles, right? You hit the obstacle, then you turn only. See? Now, boom, you hit you know that you're at the end, but you have no sensor to do that. You need to know that you hit the obstacle, which we can't really do. Huh? Okay, you get stopped, yes, but what happens if you look at Joanna's, then yes, that's what it usually looks like. So if you implement drive and then do a random turn, right? Then you think that should be good enough, but actually it doesn't, because what you notice is you always stuck very near to where you started. You never really get very far away, right? Not necessarily, because if the obstacle is close, it would hit the obstacle when the obstacle is close, right? So you cannot just go forever and then say, oh, turn every 1,000 steps, because then you hit the wall 900 times. So that would be also very inefficient, right? So, yeah. Kind of like that, yes. And this is really what happens. Let me see what mine looks like. So if you implement an algorithm here, like I do, 25% of the time you make a random turn, otherwise you drive straight, then you end up with something like this. which in my case is actually not too bad, but oops. No, that's the animation here. Some I have two different ones. In the end it looks, wait, I didn't let it run the full. So here I hit the obstacle very often, then it kind of bounces around there. And if you look at, because if you run it on Benson or Joanna's laptop, if you run it locally, it'll run a lot faster, so you can do more steps, right? And what you see is that your path kind of looks like this. But that means that you never really get very far away from the current location. And the reason for that is that in order to move far away, you need to move in this direction, and then you need to move in this direction again, and then you have to move in this direction again, right? In order to actually get away from your start position. Now the probability, in my case, because I only turn by 4 different angles, is quite low, right? Because if you have probability alpha that you stay in this direction, then probability that you do it once is alpha. Twice is, if I want to make sure that I go in this direction one step and then another step, and each step has a probability of alpha, what's the probability I actually end up 2 steps away? Huh? Alpha squared, yes. And if it takes me 10, then it's alpha to the power of 10, which is a very small number, right? Like 0.5 to the power of 10 is something in the million. So there's like a 1 in a million chance I actually be able to take 10 steps away from my start location. So that's why this algorithm doesn't work, right? And if you do this, if you plot it, I think it's convincing with my simulation and even better on the local one. You can run it for hours and it really never cleans the room, right? So you may think that, yeah, that's obvious, Jackie, this is a really dumb algorithm, but when we were doing the Urban Search and Rescue competition in 2002, this is exactly what we implemented, because for the Urban Search and Rescue Robots for Disaster competition, they told us that we need to build a robot that goes into an unknown environment, so we have no map, we have no knowledge. They told us that there would be some kind of obstacles, but they didn't tell us what kind of obstacles. Right? So it could have been like ropes and nets and doors and walls and papers on the floor and everything. And then they told us to explore this environment. So the best algorithm I could come up with was, well, I just drive and then if every once in a while I do a random turn. And not just me, but there were many other teams that implemented exactly the same thing. Now, for the competition, NIST, the American Institute for Standards, they take this kind of thing very seriously, so they built this enormously big playing field. It was like twice the size of this classroom. And it was very elaborate with like all kinds of things you would... The idea was after a earthquake, the robot was supposed to go in and look for survivors. That was the mission that we had. And a lot of teams did it teleoperated, but we thought, oh, we'll try it autonomously, at least like search the part. So we have this enormously big playing field, and there's keyboards on the ground and chairs toppled over, and then some mannequins and fake victims lie there, and curtains and boxes all over the place, all kinds of boxes, small boxes, big boxes. So we go to this competition and we start our robot, and there's this huge playing field, right? All this way. And my robot drives in like a 1 meter radius around for like 30 minutes. And just that, right? So you felt like my soul just crushed. You feel extremely stupid. And the NIST guys are all standing there expecting your robot to just zoom this through this environment and find all the victims. And all my robot does is like drive around in a circle forever in like a 1 meter radius. Not just my robot, though, I have to admit. I have to say in my defense. And so, yes, obviously, I also, at that point in 2002, I did not understand goal bias in random processes. Start bias, like the fact that that kind of algorithm is extremely biased towards your start location. And even the Roomba, the early Roomba robots, the first versions of the Roomba robot. Roomba is Rodney Brooks' company, the first vacuum cleaning robots, right? They also didn't have a touch sensor because they kind of thought, oh, that should work, right? We just drive, and then we turn, and we drive some more, and then we turn. But it turned out to be a complete disaster for vacuuming. Like, it would take years to vacuum a room, any kind of sized room, right? So that's why then they added touch sensors and much better lasers and everything after they tried this out. And this whole thing is just to give you an example of why random processes can be tricky, first of all, and secondly, why we need to have a more clever approach, which is exactly what randomly exploring random trees do. Randomly exploring random trees are solving this particular problem by creating a random tree data structure and then sampling from this tree at the edges. So they're constantly pushing the space that they're searching, they're pushing it outwards, as opposed to this kind of silly algorithm. This is really a dumb algorithm if you have implemented it once. If all the NIST people are laughing at you, it's even worse. So yes, since then we don't implement these kind of algorithms anymore. I actually did for the next year. What I implemented was a camera system because we still didn't know what the obstacles were. And touch sensors have their own problems. Like touch sensors, if you put the touch sensor here and it triggers, that's fine, right? But if the obstacle is up here and your touch sensor is down below, then your robot hits the obstacle, but the touch sensor doesn't trigger, then you didn't gain anything. If you put the touch sensor too low, so that it triggers on dirt in the floor, then it'll detect obstacles when there are no obstacles. So touch sensors aren't all that great. But they're absolutely essential for vacuuming, cleaning robots, I think, and these kind of systems. For what I implemented then for the next competition, the next year was I took a laser pointer and I mounted it on the robot straight forward, and then a camera. And then if there's ground, I can detect the laser pointer where it hits, right? So I know it's kind of free up there. And if there was anything at any height that would interfere with the robot, then the laser pointer would light up and I would detect it, and then I would turn away. So that was my version of the touch sensor. Mainly because I didn't really want to build a touch sensor. They're not that easy to design mechanically so that they work reliably the way that you want them to. But yes, it was pretty fun to have the first year urban search and rescue competition, and this big playing field, really nice, tons of things built in, and all I explored was like a 1 meter area in front where I started basically. So don't do that, read the paper on RRTs, they will explain how to solve that particular problem. Okay, good. So any other questions? Okay, good. Then I think we're done for today. Reinhard, any comments or questions? Hello? Well, maybe they left already. I cannot see the video anymore. Oh, wait, and did I share that vacuuming simulation? So once you have a touch sensor, then you can come up with much more clever algorithms, right? You can drive, if you hit an obstacle, then you make a turn. Then you just keep going straight. Then your exploration of the environment has a much higher chance of being successful. And actually the vacuuming robots, of course, nowadays have actually quite clever algorithms. Like I have to say, I'm totally impressed with my Chinese vacuum robot that we bought for $300. I forgot what the name of the company is, but that's the only robot I have anything to do with that's been running for 3 years without any problems. And its slam is amazing. Like it never gets lost in our apartment. We still have students do slam work on for their master thesis, but that's really a solved problem. Like that robot, I can put it down, it'll map this space here, no problem, it'll follow the walls, tuk, 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 with the laser thing, and then it'll clean that room here for years. You just have to clean the robot, the dust trap. But other than that, it never gets lost. Like SLAM particle filters work really well on there.